Oh, you've got satellite at home?
Yeah.
So yeah, your connection won't be fast enough to work on it.
I noticed driving in here the last few days, they're putting.
Okay, so on this one, finding the perimeter, all we have to do is add up the sides. So you've got 15 here plus 10 here. And that's the end of the easy part. Although the bottom isn't too bad, how do we find the length of the bottom? Yeah, there's 15 here, so it's 6, 15, and 15 is 36. And then we need this side here. How do we find the length of that side?
10 squared minus 6 squared will give you the inside of that leg right there.
Okay, good call. We need to find that part first, right there. And since the 6 and that missing side are the legs, if I call this A and B, this is C. 6 squared plus B squared equals 10 squared. And we could solve that. You're absolutely right. It's the square root of 10 squared minus 6 squared. Gives you what for B there?
8.
B equals 8. So that comes out to be good. So if that's 8, this here is also 8. So then we can find this length. So 8 squared plus 15 squared equals x squared. And yes, we solve that to get 17 equals x. And that's our missing side. So we add that up. What do we have there? 78? So 78 feet is our perimeter. Any questions? You look really confused, Joey.
I just don't like these.
Okay.
I like these. I hate.
What's that? It takes a lot of.
I just said I'm beyond lost, but there's not enough time.
Well, hang in there. I mean, the biggest thing with these is anytime you see a shape like this that can have right triangles cut off it, there's only two things that you can deal with when you see a right triangle. Generally, there's only two possibilities. One is you're looking for a missing side. And if you're looking for a missing side, that's where you're going to do the a squared plus b squared equals c squared. Yeah, depending on which piece you know. I always leave it like that since we know how to solve an equation. You can just solve it from there. Yep. And the difficulty, the main difficulty is your right triangles may not be apparent. Like in this problem here, the right triangle is there, but it's part of a larger piece, and sometimes it's hard to see that it's there. Of course, there's another one over here. It's the same way. You have to, and basically what I do is anytime you see a right angle that is specified, like here and here, I look to see if there's a triangle formed off of it. Now the second thing that can happen with a right triangle is you're going to be trying to find the area. And that's something we're going to be looking at today, is how do you find the area of a right triangle? We looked at angles last class, and angles are a big deal in a lot of ways. So let's say that this here is 4x minus 7, and this here is 2x plus 15. I want to find angle A. Now, looking at that, it looks confusing because what does angle A have to do with anything? Well, the hard part in many of these problems is a lot of times what you're asked to find isn't something you can find directly. Just like up here. Finding the perimeter of this, when you get to where you need to know this side here, you can't find it directly. You have to do something else to find out information that you need to know. You had to find this side first, and that involved finding this side. Once you found this side, you knew this one, and then you could find this missing side. So that's the difficulty in these problems, is letting go of what you're trying to find and looking at what can I find from what I'm given. So down here, we're trying to find angle A, but we need to back off from that and look at what we're given and what we can find from what we're given. Well, we're given these two expressions for those two angles. And we know that if we have expressions for angles, we can often write equations from those expressions if there is a known relationship between those angles. And right here, is there a relationship between those two angles? Yes. What is it?
Equal.
They're equal. Very good. So 4x minus 7 has to equal 2x plus 15. Now from there we can solve for x. Now we have this equation. The x appears twice, so what's the first thing we have to do? Get rid of one of the x's. Which one are we going to get rid of?
2x.
The 2x. We'll subtract 2x. That leaves us with just 15 over there. We subtract 2x on the other side. We have to take it from the 4x. 4x minus 2x is 2x. Minus 7.
You gotta add 7.
Then we're going to add the 7. 2x equals 22. And then
Divide by 2.
divide by 2. X equals 11. Now, obviously, that hasn't answered our question yet. We know that x equals 11, and really that x equals 11 doesn't answer the question we're trying to answer directly, but it can answer some of the other things. If this is 11, I can find this angle. 4 times 11 minus 7. 4 times 11 is 44. Minus 7 is 37 degrees. Now, just because I'm uptight and like to double check myself, I'm going to make sure this one comes out to be the same thing. 2 times 11 plus 15. 2 times 11 is 22. Plus 15 is 37 degrees. So yes, that does appear to be correct. Those both come up 37 degrees. Now that I know those angles, I can look at, can I find A? Perfect. Whichever one of them I want to use, I'm going to pick, let's pick this one for now. So I'm going to look at this angle and angle A. The relationship is they're supplementary. They add up to a straight line, or 180 degrees. So A is 180 degrees minus that angle of 37. So A is 143 degrees. So even though the information given in the problem didn't lead us directly to find what we're looking for, it led us to find something that could be used to find what we're looking for. And that's really where the difficulty comes. It's almost like a chess game. I don't know if anybody's played chess or done your reading on chess. They talk about seeing 2 or 3 moves ahead of where you're at. To really be good at it, you have to be able to do that. Well, it's the same thing here. Your next move isn't going to find the answer. So you have to be able to see a few moves down the road. It's going to get you where you need to go, so you start making those moves. Sometimes, though, you don't see that, so you just go back to what you're given and say, well, what can I find from what I'm given? And then hope it leads to something you can eventually use to find your answer. There are some of these complex problems. Like for you going into CNC, there are going to be some of those trig problems we'll do in your second semester of math, where we might, well, let's see what we can find from this, and we get to a point and it's like, oh, well, that doesn't take us anywhere near where we want to go. Let's back up and try a different direction.
Right.
I mean, you do sometimes get into a spot where you just have to cut and run and try something different.
Those are actually a lot of fun, those
Good.
I know it's weird. I'm sorry. But it was.
Well, there's a lot of research that's been done about that visualization ability. And it's one of those things that it's a skill that it's not a genetic skill. It's not an inherent. I mean, there's intelligences, and there's several forms of intelligence, have a hereditary quality to them. If your parents are highly skilled in an area, there's a better chance that you will be too. But it's a small factor. So the environmental factor is the largest thing, and it all traces back to your experiences between the ages of about 4 and 10 years of age. And if that visualization skill develops, that tends to be how people see the world, is through. That's why you hear me talking about drawing pictures and word problems and stuff like that, because that helps me. I'm a visual person. If I can look at something and see it, I can actually take that picture and I can sit there later that night without seeing it, and I can rotate it in my mind and stuff like that. And that's how I deal with problems with that picture. And so, I mean, somebody that has that skill is much more comfortable working. Now, the other side of that is somebody that didn't develop that skill, didn't practice that skill at those young ages. We get to those visual problems. It is extremely frustrating, because visualizing in a problem like this is not a skill that can develop after you get those ages. So that doesn't mean you can't learn to do it. It just means you cannot look at it, see visualize the picture and manipulate it in your mind. You have to learn, meticulous step-by-step methods of breaking it down and solving it mechanically, rather than, seeing everything at once. And there's not, from what I've seen in the research, there's not much more frustrating than trying to solve problems like that, if that's an ability that didn't develop for you. By the way, for those of you that have kids or grandkids or whatever, and you're looking at buying toys, that active play seems to be one of the biggest ways that skill develops. You've all heard about the gender gap when it comes to science and engineering careers. Has absolutely nothing to do with gender or genetics. Has everything to do with socialization. Most of the research has shown, if you take, the claim is that, young girls don't do well in math and science. Well, and there's some statistical evidence to show that there is a difference between young boys and young girls. But what research has shown is young girls who play with traditionally masculine toys like building blocks and Legos and Lincoln Logs and stuff during that age from 4 to 10 are much more likely, or actually just as likely as males, to go into those careers. So it's the toys that they play with that develop those, and that visualization skill is the biggest correlating factor as to whether somebody goes into one of those careers or not. If they don't have that visualization skill, there's a very small chance that they're going to go into one of those careers and be successful. So, as you're looking at your kids or grandkids, if you're looking at toys for them at that age range, get them Legos and blocks and stuff. Or if you don't want them to go into one of those careers, don't Legos and blocks and stuff. Okay. I don't know how I got off on that tangent, but what we're going to look at today is we are going to continue with geometry and shapes. And I'm going to start off a little bit by talking about areas. And, of course, perimeters. We have talked about both of these issues with our rectangles, but I do want to review them. Remember, we've mentioned that geometry, all of geometry, is built from one basic concept, and that's that thing right there, a point. And that point is just a location. And as we said before, it has 0 dimensions. A dimension is a measurable attribute or a measurable direction. And our next step is to take that point and, as we said, move it in a single direction. If we kept going, that made a ray that was part of our angles. But if we stop, it makes a line segment. We often refer to this as a line, but a true line goes on forever in both directions. It has no beginning, has no end. Often, though, we refer to it as a line, even though it is a line segment. A line, of course, or line segment is named after its endpoints. That would be segment AB or segment BA. Doesn't matter which order they're in. The length of that segment is equal to the distance that point moved. Remember, we started at this point and we moved to this point to trace out that segment. And since there is one direction that we can move in or one direction that we can measure in, it has one dimension. So we took that point and we moved it in one direction and we created one-dimensional object. The next step is to take that line segment. And we're now going to move it in a second direction. Now we used that term yesterday, perpendicular. So we're going to move this perpendicular to the original direction. The original direction moved along this line segment, so perpendicular would be at a right angle to that. Now if you think about it, if you take a stick and you hold it down on the sand on the beach and you drag it along the sand like that, it's going to trace out a rectangle in the sand. Because we move this perpendicular, all those are right angles. We had the original length of our line segment, and now we have moved it a distance. The size of that rectangle is called an area. And that area depends on the length of the original segment, and that distance moved. Now in a rectangle, that distance is often referred to as the width of the rectangle. So for a rectangle, you could say length times width is your area. I'm going to leave it as length times distance because in a little bit, we're going to look at things that are not necessarily rectangles and how that applies. Now, of course, this is a two-dimensional object. Since it can be measured in two directions. By the way, if the lengths here were in inches, what would the area be measured in?
Square inches.
Square inches. Inches squared. That 2 on the inches, it is squared. But notice, we're measuring a two-dimensional feature. So that 2 on the inches, that squared, is telling us that unit is a two-dimensional unit. It's measuring two-dimensional features. Whereas just simple inches is measuring a one-dimensional feature. It has a power of 1, which we don't have to write down. Well, we can take our line segment and move it to make that rectangle. Come on. If our original segment was 14 inches and we moved it here 6 inches perpendicular, what is the area of that going to be? You got it. 14 inches times 6 inches. Or 84 inches squared. But what if we go back to that original 14-inch segment? And this time, instead of moving it perpendicular, we keep it parallel, we keep it in the same orientation, but we slide it kind of off at an angle. Well, this is why I defined this area as not length times width, but a length times a distance. Because even though this side here is not perpendicular, it's not our width, we can still find an area. What we need to measure is this here, the distance that we move from where we started up here to where we ended. Let's say that distance is still 6 inches. Obviously my drawings are not quite done to scale. The area of this is still 14 inches times 6 inches equals 84 inches squared. The reason is, think of it almost like a stack of papers or a deck of cards. Here they're just stacked up perfectly straight. Over here, the pile's been pushed off to the side a little bit. But when we push it off to the side, does it change the height of that stack? No. As long as there's still the same number of cards or sheets of paper in the stack, whatever, the height of it is still going to be the same. It's just slid off to the side. Does it change the area of the end of them? No, it doesn't. So the area will still be the same. In fact, we can take that 14-inch segment and we can pull it, as long as we keep it parallel, in other words, in the same orientation as it was before, we can slide it in all sorts of weird different motions. So this might have gone like this. And as long as the distance from here to here is still 6 inches, the area is still 14 inches times 6 inches, or 84 inches squared. Because I could look at it as those cards stacked up or whatever. The stack isn't anywhere near straight, but it's still the same number of cards. They still stack to the same total height, and the area of the ends of them is still the same. It's just the pile's messed up a little bit. What does change on these, of course, is the perimeter. Here, the rectangle will have what we call the most efficient perimeter for its area. Its area is 84 square inches. Its perimeter, I can just add up the sides if I want to. Or we've been using that formula for a rectangle, 2 times the length plus 2 times the width. Either way will work. I get 40 inches of perimeter. Now notice, perimeter is just a length. So it's just inches. It's all one-dimensional. The perimeter of this one here is going to be larger than 40. It must be larger than 40. Because the rectangle is the most efficient perimeter for area. So this still has the area of 84 square inches, but it has to have a bigger perimeter. If you think about it from our right triangles, this distance here has to be more than 6, right? Because the 6 goes across here. That's what the leg of that right triangle. We can't actually find that distance right now because we don't know how far this offset is. But we know it has to be bigger than 6. Same down here. 6 is the straight line distance from side to side. So following that curve has to be longer than 6. So the perimeter there is going to be greater than the 40. Well, what if our shape is not a rectangle? Well, let's look at the first shape we can run into. As I said before, as I mentioned before, we're going to hit a right triangle. So the right triangle has that right angle in it. And let's say the bottom down here is 14 inches. And this is 6 inches. Well, this triangle is actually part of a rectangle. That rectangle is 14 by 6. That is what is referred to as the related rectangle. You don't necessarily need to know that term, but you'll hear me say it a lot. The area of that related rectangle is 14 inches times 6 inches, correct? What's the relationship between that rectangle and the triangle?
Half.
It is half. You can divide by 2. 42 inches squared. So the formula for the area of that triangle, either base times height divided by 2, or sometimes written as 1/2 base times height, like that. But it really is simply the area of that related rectangle cut in half. Now, this was a right triangle. It doesn't always have to be a right triangle. This is not a right angle up here. But this is still 14 inches. And now what we're looking at is this right here is 6 inches. The related rectangle would look like this. That triangle is still half of that rectangle. Because if I cut that rectangle into 2 pieces, here, this part of that triangle is half of that rectangle, right? And over here, this part of the triangle is half of that rectangle. So it is still half of the total rectangle. So that area is still the base of 14 inches times the height of 6 inches divided by 2, or 42 square inches. The key is, when we're dealing with areas, we must have 2 dimensions that are right angles to each other, perpendicular to each other. That 6 inches was perpendicular to the 14 inches. The reason they have to be perpendicular is they have to be able to form that related rectangle. The only shape in geometry, in math, that area is defined for is a rectangle. So everything that we find the area of has to somehow be related back to a rectangle. I'm going to give you one to try in your notes here. So that's 7 feet there, 25 feet there. Find the area. Well, now, if you had a couple seconds to think about it, are we going to do 7 times 25 divided by 2?
No,
Why not?
because we need to find the length of the base.
Okay. We have to have 2 dimensions that form a right angle. Those do not form a right angle. This side, along with the 7, forms a right angle. So this is the side we need to know. We call those sides A and B. The 25 is side C. A squared plus 7 squared equals 25 squared. Side A comes out to be 24 feet. We're going to do second square root, right? Again, most of you have to have open parentheses come up there. 25x squared minus 7x squared. Make sure you close your parentheses. Comes out to 24.
I did something.
Okay. So now to find our area, it's 24 feet times 7 feet divided by 2, 84 square feet. Well, we're talking about perimeters and areas. Of course, the perimeter of that triangle can be found by adding up the sides. And now that we know that Pythagorean theorem, a squared plus b squared equals c squared, we can find the missing sides we need to add up the sides for a triangle. There are methods for finding the area of a triangle that does not have a right angle in it and does not have a height given. For this course, we're not going to get into them. If you're in a trades course like construction or machining, we will get into those in those classes. But for the most part, if you're not in one of those programs, you don't necessarily need to be able to find odd triangles. So we're going to move on to circles. A circle is completely defined by two features. The first feature is its center. The second feature is the distance from the center out to the edge, which is the radius. Now there's another feature of a circle that doesn't define it. It's once the circle's defined, it can be found. It's called a chord. A chord is a line segment that has its endpoints on the circle. What we're going to be most concerned with is a very special chord that contains the center of the circle, which is called a diameter. Good. There is a relationship between the diameter and the radius. We use D for diameter is equal to 2 times R, 2 times the radius. A couple thousand years ago, obviously they didn't have television and video games, so they had a lot more time on their hands. Mathematicians messed around with the circle, taking the diameter of the circle here and then trying to wrap it around the outside edges of the circle to see how many times you take that, how many times that diameter would go around the edge of the circle. And at first they thought it was 3 times, but they found out later it wasn't quite 3 times. What they found was the the circumference of the circle, the distance around the circle, which is called the circumference, divided by the diameter, was not a very nice number. It was a decimal that went on forever. That is pi. It's actually spelled just P-I, but it's pronounced pi, just like apple pie or whatever. It doesn't end and it doesn't repeat. There is no predictable pattern. And we talked about repeating decimals, where some of them we took out 5 or 6 decimal places before they started to repeat themselves. Pi never does. They've calculated it out to tens of thousands of digits, and it's never repeated. They've never found any sort of repeatable pattern with it. So it's what we call an irrational number. It cannot be made into a fraction. It does not repeat. It just goes on and on forever, never ends. So pi is actually defined to be that ratio of the circumference divided by the diameter. So if we rearrange this formula here, the circumference, C, can be found by taking the diameter times pi. Just multiplying by diameter on both sides and getting rid of it. Most of the time in this textbook, my math lab is going to use 3.14 for pi. I don't know where the 5 came from. 3.14 for pi. But be careful. Read the problems. Make sure you see what it says to use for pi. Other things that sometimes get used for pi. 3.1416 gets used sometimes. 22/7 gets used sometimes. Now, since there's this relationship between the diameter and the radius, the circumference is sometimes defined, instead of diameter times pi, is 2 times the radius, which is equal to the diameter, times pi, right? Does that make sense? That is sometimes rearranged to look at that, 2 pi r, 2 times pi times radius. So in a circle with a diameter of 8 inches, how do I find the circumference?
Yeah, multiply 8 times 2.
8 times pi. 8 is the diameter. So it's just going to be,
4 times 3 times 5.
yeah. So 8 times pi is 25.12 inches. In a circle with a radius of 5 inches, how do I find the circumference?
2 times 5 times 5.
2 times 5 times pi. Very good. Which comes out to be 31.42 inches. Or if we're using 3.14, 31.4 inches. If I give you that a circle has a circumference of 50.24 feet, what's the diameter have to be? Well, we know, there we go, that's exactly right. Circumference is diameter times pi. If I'm going to solve that for the diameter, I have to divide by pi. So the diameter is that circumference of 50.24 divided by pi. I'm just going to write in 3.14 for pi. That divides out to be 16 feet. Any questions so far? Well, then we can run into the area of a circle. That little symbol I put by the capital A is just a little circle. Can anybody tell me the formula for the area of a circle? I'll give you a hint, there's pi in it. Pi times...
Diameter?
Careful, that's circumference, pi times diameter.
Oh, the radius?
The radius squared. There we go.
Oh.
Pi r squared, remember? Is there a formula for area of a circle? Well, where does that come from? Well, to get it for you exactly, I would have to use calculus. And we don't really have the 3 or 4 weeks it would take me to go through the basic calculus to get you to understand that. So I'm going to do kind of a rough, I'm going to abuse my calculus a little bit and give you kind of a rough demonstration of where that formula comes from. I am going to cut my circle in half, and I'm going to take that half circle. And of course, this circle here has a radius of r. The circumference of this whole circle is going to be 2 times pi times r, correct? What's going to be the distance around this half circle? 2 times pi times r divided by 2, right? It's only half. Well, the 2's cancel out. That distance is just pi times r. So I have that half circle. And here's what I'm going to do is I'm going to slice it in as thin little pieces as I can. Oops. And I'm going to slice them in very uniform, very the same thickness, but very thin little slices. I'm going to take those little slices, I'm going to fan them out. Pretend those are all uniform. Now I'm going to take the other half circle down here. I'm going to do the same to it. I'm going to cut it in equally thin slices. And I'm going to fan them out, and they're going to slide right in and fill in these gaps. There's that rectangle. Fills it right in. Well, this distance right here is what length? That's just my radius, right? This distance here, if I cut these thin enough, is just this distance around the half circle. Pi times r, right? So what we have here is we have a rectangle that is pi times r in length and a width of r, so pi times r is pi r squared. Where that area formula for a circle came from. Now, like I said, I was very sloppy in my calculus there, but that's how you come about that. That's really all calculus is this here slicing stuff into thin enough slices that you can rearrange it into a shape that you know. That's maybe a slight oversimplification of it, but that's basically what it all comes down to. So I have a circle with a 10-inch diameter. How do I find its area?
Pi times 5 squared.
Ooh, nice catch. I was waiting for somebody to say pi times 10 squared. Why is it 5 and not 10?
If the radius is half of the diameter.
Exactly. The diameter is 10. The radius would be half that, or 5. So pi times 5 squared is going to be 78.5 square inches. If I have a circle with a radius of 4 feet, how do I find its area?
Pi times 4 squared.
Pi times 4 squared. If I use 3.14 for pi, that comes out to be 50.24. What's my units going to be?
Square feet.
Squared.
This will be feet squared because we started out with feet. Right? That's why I did that, is I wanted to see if I could catch you on it. If I give you that a circle has an area of 12.56 square inches, I want to find the diameter. Well, our formula here is area is pi times radius squared, correct? Do I know the area?
Yeah.
It is 12.56. Do I know pi?
Yeah.
We'll use 3.14. Well, there has to be something I don't know, so I'm assuming that's the radius. So we're going to start out by dividing by pi. So 12.56 divided by 3.14 is 4. Over here, the pi's are gone, so it's just radius squared. Now, we did solve equations similar to this in our Pythagorean theorem. What do we have to do to find r? Do the square root. The square root of 4 is 2 or negative 2, but negative 2 wouldn't make any sense. Our radius is 2. Now we got to go back and make sure we're answering the question. This was in square inches, so this is 2 inches. Is that answering our question? No, we want the diameter, which would be 4 inches. Double the radius. In real life, in the real world, geometry is not about rectangles, triangles, and circles. But geometry in the real world can be broken down into those shapes. We might have something like this. We're asked to find the area and perimeter. Well, let's start out with the area. To find the area, we need to break this down into shapes that we know. Shapes that we know are...
Square and a half a circle.
We have a rectangle and a half a circle. So I'm going to cut this right across here. I'm going to call that piece 1 and this piece 2. Piece 1 is a rectangle. What are its dimensions? 5 by 8 or 8 by 5. Multiply those up to get an area. 40 inches squared. That's piece 1. Piece 2 is a circle. Do we know its area, of course, is going to be pi times radius squared. Do we know its radius? 4 inches. Right? Yep. 8 would be the whole diameter, and that is a very common mistake that's made right there. Now, of course, it's only half a circle, so we're going to divide this by 2. Pi times 4 squared is 50.24. Divided by 2 is 25.12 square inches. So we add those together, you get 65.12 square inches. Any questions there? Next is perimeter. Well, I'm just going to start out here. I got 5, 8, and 5, right? So I'm going to add those up. Now, a lot of people ask, well, what happens to the 8 across here? Well, is that the perimeter, remember, is the outside edge.
Right.
That isn't part of the outside edge. That's inside the shape, so it's not part of the perimeter. The only piece that's left is the half circle. To find that, we're going to find the circumference of the whole circle, which is pi times 8. Pi times diameter, right? Which would be 25.12. But then, yes, we are going to divide that by 2. We get 12.56. Why did we divide it by 2? because it's only half of the circle, half of the perimeter. So we add 5 plus 8 plus 5 plus 12.56 is 30.56 inches. Well, I think you are ready for me to have you try one of these new notes. I'm going to give you a half circle, the diameter of 10 feet. Find the area and the perimeter. I'll give you about 2 minutes here. For the area, somebody walk me through it.
Pi times 5 squared.
Pi,
By 2.
perfect. Pi times 5 squared and then divided by 2. The 5 comes from the fact that 10 is the diameter. We need the radius, which will be half that, of 5 feet. So pi times 5 squared divided by 2 is going to give us 39. Perfect. So once in the calculator, 3.14 times 5 squared divided by 2. We don't have to do anything special for the dividing. 39.25 is exactly it. What's the units? Careful, yes.
I always mess up on that.
Well, and I do a lot of examples in inches, so I like to throw one in feet in there every now and then, just keep you on your toes. The perimeter then has 2 pieces to it. First, we have the circumference part of it, which will be pi times 10, and then divide by 2, which is going to give us 15.7 divided by 2. No, 15.7. Just 15.7. And that is in feet. But where's the second part that I still need to add to that? What I just found there was this arc around the half circle. I have to add the 10 feet, which is what most people will forget now. So that is 25.7 feet of perimeter. Me? No, I'm not for some reason. It's kind of frustrating. Oh well. I don't have my format flip here either, do I? Nope. They won't let me flip it because there's more than one line there. Because I screwed up. Oh well. That's okay. We'll just do it the old-fashioned way and we'll make it ugly. I'm actually, because I'm right-handed, I'm much better drawing circles, half circles on that side of the page than on this side of the page. It's a racetrack. So what we have here, we have a straightaway that's 200 feet long. The total length of the track is 280 feet. The width from here to here . I'm going to make it easy on us. I'm going to go 30 feet. I want to know the area, the outside perimeter, and the inside perimeter. Now the outside perimeter, of course, is around the outside. The inside perimeter is around that inside piece. This looks like a monster problem. It looks ugly. It's not. But again, it comes down to that visualization. You know, being able to take pieces apart and move them and put them back together. Most of you probably see that we're going to have to cut it like this. Get the circular parts away from the rectangular parts. And then we have 4 parts here for the area. 1, 2, 3, and 4. Well, 1 and 2 are identical. So are 3 and 4. Part 1 is just a rectangle that is 200 feet by 30 feet, which is 6,000 square feet of area. Part 2 is also 6,000 square feet of area. So it comes down to parts 3 and 4. How do I find the area of this weird little shape? Well, the answer is, by itself, I can't. But I can take this other weird little shape on the other end that's its mirror image. If I take that off of there, that messed up on me a little bit, but that's okay. What I have there, if my artwork was a little more passable, is I have a big circle with a little circle cut out of the middle. Basically a donut. And its area is found by finding the area of the big circle. What's its radius going to be? Well, from here to here is how much?
40 feet.
Yeah, 40 on each side. So it'll be 80 total, 40 on each side. So 40 is the radius of that big circle. So that's going to be pi times 40 squared, which is going to give us 5,024, I believe, square feet.
You say so.
If I say so. A little bit trickier is, what's the radius inside this little circle?
Well, you know the outside part is 30 feet.
You know from here to here is 30. Very good. So 40 minus 30, that has to leave 10 feet there. Perfect. Now I'm going to pause. Does everybody see where that 10 feet comes from? Any questions where that 10 feet comes from? If it's 40 all the way out, and you're given here that this thickness is 30, 40 minus 30 leaves us with 10 feet. So that area, pi times 10 squared, otherwise known as 314 square feet. There you go. We subtract that, we get 4,710 square feet. Not 2.
Oh, because we put them all together.
That's the 2 of them together. You got it. So that adds up to 16,710 square feet of area. Not so bad? Not as bad as it looked like it was going to be? Okay. Outside perimeter. Well, outside perimeter, I have this, which is 200 feet. This, which is 200 feet. Then these two pieces, I can refer down to here, is just the circumference of one circle when I put them together. So outside perimeter. I'll put perimeter, and I'm just going to put outside down here. There's 200 plus 200 plus, that is going to be that circumference 2 times pi times 40. Why times 2? Because the 40 is a radius and circumference is pi times diameter, which is 251.2 feet. My outside perimeter is 651.2 feet. Inside perimeter. If I look at that, well, this is 200 and this is 200, and these two form this little circle in there. So that'll be 200 plus 200 plus that circumference is 2 times pi times the radius of 10, which is just 62.8 feet. So the inside perimeter is 462.8 feet. Where did the 10 come from? Right here. 10 is the radius of that, so that's why it had to be 2 times pi times 10, because we had a radius, so you're multiplying by 2 to make it a diameter. Any questions? You've got that dazed look.
Uh-huh.
Don't understand it or just don't like it?
Both.
Both? Where'd I lose you?
Huh?
Where'd I lose you?
At the beginning.
Are you okay with basic circles before I start combining them with other shapes?
Oh yeah, I can understand that part. It's just the outside, inside. And
Oh.
trying to
The outside, inside. Do you understand how the biggest thing here is understanding that I was able to cut these ends off and make this donut shape. The outside perimeter, inside perimeter, if you don't get the difference between those, that's not a big deal.
I think it's with all the steps that you're doing.
There are a lot of steps to these.
Yeah.
And the stuff we're going to do in the second hour, there's going to be a lot more steps. Unfortunately. That's one of the things I've learned through the years is draw the pictures as big as I can, because you start cutting them apart and things get small very quickly.
Yeah.
About the same as what I have here. Pretend all those corners are square. Oh yeah, we're going to make a mess here for a minute. You know what? I'll let you guys figure that out. First thing I want to do is there are two missing dimensions here. A and B. I want to find those missing dimensions. So let's find A. Well, what I'm going to do is I'm going to do some reference lines here. Remember, length is distance. If I'm asking you to find the length of point A, I'm asking what's the distance from here to here. So how far away is this point from this line, this yellow line? Well, I can't, its distance away is the length of A, but I don't know that length, so I've got to find another way to get there. So I'm going to go here. How far am I away now? 8. Then I go another 20. How far am I away? 28. Then I go here, and I'm at 46. So right here, I'm how far away still? 46. Yeah, so that puts me at 38. So A is 38 feet long. Does that make sense how I did that? I picked an end, I picked a side. This was a horizontal dimension I was looking for, so I'd use a vertical reference line perpendicular to it. And I'm measuring distance away from that perpendicular reference line. Now to find B, I'm going to do a similar thing, only this is going to be my reference. How far am I away from right here? 2. How about here? 18. Very good. 2 plus the 16 is 18. Here?
22.
Perfect. 18 plus 4 is 22. How about here?
22.
Still 22. Here?
-8.
Minus 8 gives us 14. So B is 14 feet. So we found those two dimensions. That is a skill that students really struggle with. That again is that separation between that visualization ability and then or coming up with some sort of a coping skill to deal with it. Now that we have those dimensions, what I really want to find here is the area of this piece. You knew it was coming, right? But without those dimensions, the area would have been pretty tough. Now, so far, what we've done for areas, we've chopped things into pieces. Now, I suppose I could cut this across here, here, and here, and make those 4 rectangles. What's this one up here going to be? 20 by 4, so that is 80 square feet. I'll call this one number 2. 14 by 8, otherwise known as 112. I'll call this one 3. 3 is not so simple. This length,
30.
this one's 30. You got it. 38 minus 8. And this is 16 plus 2 is 18 there. Yes. So that was just finding the dimensions. There was the tough part. 30 by 18 is 540. And finally, the fourth one here is what dimensions? 8 times 16, 8 by 16, 16 by 8, either one. 128 square feet. Which all adds up to a lovely 860 square feet. Sound right? That's good from where you're at. You'd rather trust me than try to do them? Well, that was, it wasn't horrible. But there's another way to do it that some people might find easier. And that way looks like this. I'm going to make that a big rectangle by filling in the missing corners. This big rectangle is 38 plus 8 is 46 feet. by 2 plus 16 is 18 plus 4 is 22 feet. So that large rectangle is 46 by 22, which I believe is 1,012 square feet. Does that look right? I double check that one. It's a Tuesday. Yes, it's 1,012. But that's bigger than the whole thing because I put in extra pieces. So I got to subtract out 8 by 8. 64 square feet. If I subtract that out, I am left with 948. Then I've got a 4 by 18. Otherwise known as 72 square feet. If I subtract that out, I've got 876 square feet. And finally here I've got a 2 by 8. (16 square feet). I subtract that out. I have 860. Same answer. Two different ways to get to it. Some people might find it easier to do what we did here. Cut it up. There, and there. Add them together. The difficulty there was finding those missing dimensions. Especially in this middle piece here. Finding those dimensions was a little tricky. Others might find it easier to make it one bigger piece and subtract the stuff out. That's the way I think, is if I can fill in little corners and then subtract them out later, it makes more sense. But that's my construction background of if I'm estimating, if I have a floor of a building that looks like that and I'm estimating, I'm just going to figure out the big rectangle and count those corners as waste. I'm not going to bother subtracting them out. So that's how I think. But there are obviously several ways to do it. It seems like a good point right now to take a break. So take about 10 minutes. Let's come back at about 10:28. It's almost 10:18.